Dear students, this is the second session for Module 5 of EC206 Computer Organization. This session is being prepared by myself, Bonifus, Mr. Ronnie Anthony, and Anita. In this session, we will see more details about memory systems in a computer. Memory systems. Normally, processors will be having very high speed. It will be operating at very high clock rate, and most of our data will be stored in hard disk. When compared to processor, this hard disk will be very slow. So we need some mechanism to gap between the speed of this processor and our main storage of hard disk. For that, we will be using a series of memory systems that we will see in detail. So traditionally, for a memory system, processor will communicate with memory. So processor sends an address over the address bus to the memory system. Now, the memory operation, it may be either read operation or write operation. It's a write. For a read operation, the memory write signal should be 0. That is, write enable will be 0. And memory returns the data on the read data bus. If it's a write operation, memory write signal should be 1, and the processor sends data to the memory on the write data bus. Now, when we are interfacing processor with memory, some conventions are there. Normally, processor will be sending some k-bit address. So, k-bit address means memory we can have up to 2 raised to k addressable locations. Now, our data size may be of n bit. That means each location in the 2 raised to k locations can store n bit of data. It is called word length. Now, our operation may be read, write, or something else. So, for that, we need some control lines that will give the signals for read or write, some other operations also. Most of the memory systems will work based on two principles. First one is temporal locality. Temporal locality means, suppose we are going to access a particular location. Then there is a chance that we are more likely to access that location again. That principle is called temporal locality. Now, spatial locality is there. Spatial locality means we are going to access one particular memory location. Then it is more likely that we will be accessing the nearby locations. Memory systems use a hierarchy of storage to quickly access the most commonly used data, while still having the capacity to store large amounts of data. See, when we are talking about memory hierarchy, ideally, computer memory system should be fast, large, and cheap. But in practice, a single memory only has 2 of these 3 attributes. That is, it is either slow, small, or expensive. That is, if we consider the case of hard disk, it will be slow. If we consider the example of cache, it will be expensive. But computer systems can approximate the ideal by combining a fast, small, cheap, and a slow, large, cheap. This is a typical memory hierarchy. Near to the CPU, we will be having cache. So, processor will first check whether data is available in cache. Normally, cache will be very small memory. It can accommodate only very few locations. So and this cache will be now incorporated within the CPU chip itself. Now if data is not available there in the cache, processor will check it in main memory. If data is not there in main memory, then processor has to fetch data from hard disk to main memory. Then it needs to access it from main memory. Then it will become a slow process. This is another view of memory hierarchy. So in the y-axis we are having speed, and in the x-axis we are having capacity. So top in the hierarchy we are having cache. It will be having very high speed, but capacity will be very, very less. Main memory we will be having some intermediate speed and some intermediate storage. And the last and the bottom in the hierarchy will be having virtual memory that consists of hard disk. It will be having high storage capacity, but speed will be very less. And cost-wise, cache should be expensive, main memory moderate, and virtual memory will be cheap. I will see some of the characteristics of memory. We can categorize a memory based on different parameters. First one is location, that is where that memory is there. Whether it is internal to the chip or external to the processor. If it is internal to the chip or the motherboard, we can call it as registers, main memory, cache, etc. If it is external to the motherboard, it will be optical disk, magnetic disk, tapes, etc. Normally, internal memories will be faster but expensive, but external memories will be slower and cheaper. And external memories having high storage capacity when compared to internal memory. The second parameter we are going to compare is capacity of data it can store. This is small memory, something like internal memory. Normally we will be talking about number of bytes it can store. If it's a large memory, normally we will be talking number of words it can store. Then the unit of transfer. This is small memory, we will say number of words it can transfer per time. It's a large memory, normally we will be considering number of blocks it can transfer. Block means a set of words. Now, inside the memory, we are having different word addresses, and corresponding to each word address, we are having some storage location. So, for corresponding to a location, we need to access a particular location. For that, we are having different access methods. If it's a sequential memory, we will be having only one read or write mechanism, and we will be having some 2:k address of locations. So once processor sends an address, this read or write mechanism will compare each address one by one, and if there is a match, it will perform a read or write operation. Normally, this type of operation will take more amount of time, but cost-wise, its implementation will be lesser because we are having only one read or write mechanism. Now there is another mechanism which is called direct access method. In direct access method, if you are having 2:k address locations, we are having 2:k read or write mechanism. So for each address, we are having a dedicated read or write mechanism. Definitely, our speed will be higher, but implementation cost will be very, very high. Now there is another mechanism which is called random access. In random access method, again we'll be having only one read-write mechanism. But when compared to sequential mechanism, in sequential we had a sequential search for the address match. Here, that address match search will be in a random fashion. So sometimes it will give better result than sequential search, sometimes may. But in practical, random method is more efficient than sequential method. Now, associative access method is there. In associative access method, we will be grouping different addresses to a particular set. Something like we are having two HTTP address locations. We may group it into 3 sets. So each set will be having one read or write mechanism. And inside that read or write mechanism, we need to program. Inside that set, we need to have sequential search or random search. Next is performance. Performance, we can have access time. Performance will normally becomes in 3 parameters: access time, cycle time, and transfer rate. And these 3 parameters are related by the equation En equal to Ta plus N by R. So Tn is the average time to read or write n bits. Ta is the average access time. N is the number of bits. R is the transfer rate in display file. Now, another characteristics of the computer memory system is what is the physical type. We can have semiconductor memory, something like solid state drive. Then we can have magnetic storage, something like floppy disk. We can have optical disk like CD, DVD. Then we may have magneto-optical types also. And next characteristics is physical characteristics. Our memory can be either volatile or non-volatile, or erasable or non-volatile. One volatile or non-volatile means even if we are removing the power, the data will be lost. That is called volatile memory. Non-volatile memory means even if we remove the power, our data will be vacant. It is called non-volatile memory. Now, erasable memory and non-erasable memory. Erasable memory means something like our rewritable CDs and DVDs. And means once we write, we can erase that data and we can restore some data. Non-erasable memory, something like normal CDs and DVDs. These we won't be able to rewrite the data. And finally, organization of memory, that we'll see in detail. Normally, we will be having 1-bit storage. How we are organizing this 1-bit storage elements to store a large memory? It is called organization of memory that we are going to see. First, now we will see one equation. Now we will see memory system performance analysis. The performance of memory system metrics are being analyzed on miss rate and hit rate. And based on miss rate and hit rate, another parameter is called average memory access time. Miss rate means number of misses divided by total number of memory access, which will be equal to 1 minus hit rate. So, suppose we are our processor is going to take some data from cache. and processor is giving some is trying to attempt some 5 access from the cache. Assume that out of this 5 access we had only 3 data. 3 data was there in the cache. Then number of misses is 5 minus 3, which is 2. So number of misses will be 2 and total number of memory will be 5. So this rate will be 2 by 5. Similarly, hit rate will be number of hits divided by number of total memory access. So in the example we considered, it will be 3 by 5, which will be equal to 1 minus miss rate. And here we see the different times in the average memory access time of A and B. First one is the key cache. That means processor needs to access data from the cache. The time required to access the cache. So if data is not there in the cache, there will be miss rate from the cache, which is called by MR of cache. If miss rate is there in cache or miss is there in cache, we need to access the data from main memory, which is called by key. If data is not there in main memory, definitely we will be having miss in the main memory. We need to access data from the hard disk or main memory, from the virtual memory, hard disk or virtual memory. So if data is not there in the main memory, we will be having miss rate for main memory. This is called MR. If miss rate is there for main memory, we need to access from virtual memory, which is TV. Where Tcache, TMO, TVM are the access time of the cache, main memory and virtual memory. MR cache, MRMM are the cache and main memory mistakes. Here we will see organization of semiconductor memory. So first we will see organization of 16 into 8-bit memory. Or we need to store 128 bits, 128 bits, and we need to access this data as 8-bit elements or byte elements. So 128 divided by 8, we will be having 16. So each row will be having 8 bits, 0 to 7. That is named as B0, B1 to B7. And we will be having 16 rows. It is indicated as W15 to W7. Now, each of the square boxes indicate 1 bit storage. That 1 bit storage can store either bit or bit complex, which is indicated as B or B complex. It is B0 or B0. Now, at the output or input port, we will be having sensor write circuit. Sensor write circuit is nothing but read or write circuit. So based on the read or write signal, data is either produced on the bit lines B0 to B7 or data will be taken from the bit lines to storage. As we are having 16 rows and we are going to implement it as a 16 into 8-bit memory. That means at a time we need to access 8 bit. At a time we need to access only one of these 16 rows. For that we will be having a 4 to 16 address decoder. We have 16 rows, so the address decoder will be having 4-bit number. 2/4 we will get 16. So the address decoder will be having inputs A0, A1, A2, A3, 4 bits. So based on this input, we will be selecting one of these 16 rows. That's from W0 to W50. Now, based on the rows selected, we will be having data available in B0 to B7, or we will be writing data from B0 to B7 to that corresponding for organizing a memory 16 into 8-bit fashion. That means we are having 16 rows, and at a time we will be taking or writing, reading or writing 8 bits. We need to have, we'll count the number of bits. First of all, we need to have 4 address bits, A3 to A0. Then we will be having 8 data bits, B0 to B7. So 4 plus 8, 12. Then we will be having read or write signal and chip select for CS. So 8 plus 4 plus 2, 14. Then we will be having 2 pins for power and ground. The total will be having 16 pins. Suppose in a similar fashion, we need to store 1k bits of data. That is, you need to store 1024 bits of data. If in the similar fashion we are going to implement it, that means at a time we need to take 8 bits of data. 1024 by 8 we will be having 128 rows. So if we need 128 rows, we need 4 address lines. We need 7 address lines. That is 2 raised to 7 is 128. We need A0 to A6. Then our pin number will be increased by or increased to 90. So if we have limitations on that pin number, we need to go for some other organization. On that one type of organization. Next slide. We need here we need to store 32. We need to store 10. So if we are organizing our 1024 bits as 128 into 8, we will be having 19 bits. Suppose due to our manufacturing limitations or something, we need to reduce the number of bits. For that we can go for some other organization. We can store 1024 bits as 32 into 32 bits. So 32 into 32 against 1024 bits. And to access this 32 into 32 bit memory, we need to have a 5-bit decoder. This 2 raised to 5 is 32. So output of this 5-bit decoder will be based on this 5-bit decoder input value, one of the 32 rows will be selected from the memory, and each row will be having 32-bit elements. Here we are going to organize it as a 1k into 1 bit memory. That means from this 32 columns, so 32 bits in a single row, we will be selecting only one particular bit. For that, we will be using F32 to 1 output mux1 input dmux. So that is shown over here. And for this mux or dmux, we will be having a 5-bit selected because here we are having 32-bit. So if we are organizing our 1k bit memory element like this, how many pins we need? We need 5 bits at the decoder input, 5 bits at the multiplexer select, so total 10, 5 plus 5, 10. Then our output or input will be at a time only 1 bit, so 11, 10 plus 1, 11. Then we will be having read or write and chip select, so 11 plus 2, 13. And we will be having power and ground. So 13 plus 2, 15. So instead of 9 inches, by this implementation we can reduce it into 15 bits. So we have said that we will be having a basic 1-bit storage element. Now we will be seeing what is that 1-bit storage element. That 1-bit storage element can be either static memory or dynamic memory. First we will see static memory. This is static memory. We will be having two inverters connected back to back, and we will be having two transistors T1 and T2. These T1 and T2 are NMOS, and the gate of these NMOS are connected to a word line, and B and B dash are bit and bit complement line. For read operation, what will we do? Well, we will give word line as high. If word line is high, that is connected to the gate of the NMOS T1 and T2, that means transistors T1 and T2 will be on. So whatever data is stored in this inverter latch, that will be available at the points B and B dash. So X will be available at B and Y will be available at B dash. For write operation, what will be doing is that what data we need to write, that data will be provided on the line B and its complement will be given on the line B complement. Then we will activate the word line. Then that data will be stored in the latch. Now we will be seeing a more detailed view of this static memory. We are having two inverters. These inverters, we can connect it in CMOS technology. So in CMOS technology, each inverter will be having a PMOS and an NMOS. So this is shown over here. Here we have two inverters. So first inverter will be connecting using one NMOS and PMOS. Second inverter also will connect using one NMOS and PMOS. Shown over here. And this is the gate for the first inverter, and this is the gate for the second inverter. Now we will be having two states. State 1, that is x equal to 1 and y equal to 0. If x equal to 1, that 1 is fed to gate of T6 and gate of T4. That means if NMOS gate is 1, that NMOS will be 1. And if PMOS gate is 1, PMOS will be off. If PMOS gate is 0, PMOS will be on. If NMOS gate is 0, NMOS will be off. So if x equal to 1, T6 which is an NMOS which is on, and T4 which is a PMOS which is off. And in the state 1, y is equal to 0. So as y equal to 0, T3 will be on and T5 will be off. If it is state 0, x is 0 and y is 1. So x is 0, 0 is at the input of gate of T4. So T4 will be on, T6 will be off. Y is 1, that means T5 will be on and T3 will be off. Now we will be talking about dynamic plans. So before that, static memory is the advantage is that it is having high speed and we don't need periodic refreshing. But the disadvantage of the static memory is that to store a single bit of data, here we are having 6 transistors. So that is not economical. So we need some other memory solution which is called dynamic memory. In dynamic memory, instead of 6 transistors, we are having only 1 transistor and 1 capacitor. Here, data will be stored as a capacitor charge. And we will be checking the value voltage at the capacitor. If it is above a threshold, that will be treated as 1. If it is below a threshold value, that will be treated as a 0. But the disadvantage of dynamic RAM is that we need to periodically refresh the data inside the capacitor. Otherwise, our data will be lost. That issue is not present in static RAM. For example, suppose we are storing a value as 1. That means the value stored in the capacitor should be above a threshold voltage. But the capacitor will discharge and it will lose some value from the voltage. So if we lose that value, that will be treated as a 0. To avoid that, we need to periodically refresh the data in the diagram.